Hi everyone, I'm really excited to be presenting one of my favorite AI topics on program synthesis using genetic algorithms. So just to get started, I want to quickly introduce myself. My name is Kory Becker. I'm a software developer at Bloomberg. I design web applications and web services, although my core interest in computing has always been artificial intelligence and data science. I'm also the author of the book, Building Voice-Enabled Apps with Alexa, which is my first published book in 2017. The book talks all about how to create conversational UI and chatbot technology for the Amazon Echo device. The book is available on Amazon and Safari Books. And to start this off, I do consider myself an AI enthusiast. I've always been fascinated with artificial intelligence, especially the idea of a computer program being able to write its own computer programs. This interest drove me into research and investigation into how program synthesis could be achieved through the usage of genetic algorithms with a variety of different programming languages. My initial attempts with using common languages such as BASIC, C++, and Java using evolutionary techniques were initially unsuccessful. I believe this was largely a result of a complexity of the number of instructions in the language, as these programming languages are initially intended for interpretability and usage by humans rather than computers. AI Programmer, however, is a system that I developed that can automatically generate full software programs with minimal human guidance through the use of a tightly constrained programming language that consists of just a very small number of instructions, making it particularly suitable for evolutionary techniques, and it's yielded some surprising results. At the core of the system, the user provides a goal for the program in the form of a fitness method. The content for the fitness method can include training examples or unit tests for scoring the performance of the resulting programs. A programmer begins from a completely empty state and evolves programs by manipulating the language instructions. This system facilitates integration with evolutionary techniques as it limits the number of instructions and reduces the overall search space for the genetic algorithm. Let's take a broader look at how the system works. At the core of AI Programmer is the task fitness function. You can see this in the up left corner of the flowchart. The task fitness is implemented within the AI Programmer framework, specifically using C#.NET, which is what the framework is written in, and provides the system with instructions on how well a resulting program that gets generated performs for solving the task at hand. Upon initialization, the system generates a random population of genomes. During each generation, genomes are mapped to the corresponding instructions within the programming language. You can see that under the heading for generational genome mapping in the flowchart. Each genome, which now represents a program, is executed and scored according to their functional value against the task fitness as specified by the user. Scoring occurs by running each program using an embedded interpreter. You can see that in the top part of the flowchart within the system. This facilitates speed of execution, as well as for allowing for security and expandability in the programming language itself. After scoring or genome functional analysis is complete, the best performing genomes are carried forward into the next generation, while poorly performing programs are eliminated from the pool. You can see this under survival of fittest selection in the bottom, following which output from the best performing program is displayed to the operator, allowing a view into the performance of the generating process over time. The final step of the generation is to construct new offspring by choosing parent genomes and applying crossover and mutation. The cycle repeats by mapping each genome to programming instructions, executing, and assigning fitness until a solution is found. Let's take a look at the details behind the programming language used by the system. So AI Programmer utilizes a programming language that is easy to manipulate and construct with. The selected programming language is very strange and esoteric. In fact, it's very difficult, almost impossible, for humans to understand and use. However, its simple nature makes it perfect for a system using genetic algorithms to utilize, and it contains three key qualities that make it perfect to use in the AI Programmer system. The first key quality of the programming language is that it is Turing complete. This means a Turing complete programming language is one that is theoretically capable of solving any computational problem in the universe or that computing can be applied to. This means, by extension, that the AI programmer system using a Turing-complete programming language can itself theoretically construct programs to solve any potential computational problem solvable by computers. This opens the door wide open to the type of solutions that could be created using a software system such as AI Programmer. The second key quality about this programming language is that it consists of just 8 instructions, 1 byte each. That's the entire programming instruction set right here in the slide. The shift up, shift down, plus, minus, dot, comma, open and close brackets. Those are all the instructions in the programming language. This makes it easy for genetic algorithm to manipulate, as the number of possible instructions are kept to a minimum. The third key quality of this language is that it's easy to build an interpreter for and to expand upon. Since we're working with such a small number of instructions, it's very easy to alter the programming language or extend it, as well as to write an interpreter and integrate it into the system to execute the programs. To generate a program, we first create a genome. The genome is encoded as an array of floating point values. Each value corresponds to a programming language, an instruction in the language. The genomes are converted to a program, executed, and their fitness is ranked according to the output of each program. The closer a generated program comes to solving a particular task, the more likely it is to continue to the next generation. At each generation epoch, we use roulette selection, crossover, and mutation to create child programs that are slightly different and hopefully better than their parents. Let's take a look at a more detailed example of the mapping of a genome. So here's an example of constructing a genome from an array of floating point values. Notice how each value maps to a specific instruction in the language. Initially, these values are all random, and the programs won't do much except throw errors and fail, most likely immediately. However, 1 or 2 of these are bound to run and do at least something, and it's these that will move on to produce offspring with code that gets better and better over time. So in this example, you can see how the instruction 0.6, the value 0.6 maps to the programming instruction plus, which is an increment operator in the language. Likewise, 0.1 maps to a begin loop instruction. And this is how we map floating point values to the actual instructions in the language. To create offspring, a parent genome contributes part of its genome to the child. This is called crossover, and you can see it in action in the slide above. We can also apply random mutation, which slightly modifies the value of a particular gene, resulting in a corresponding change to the resulting programming instruction. Now, these changes can copy forward potentially beneficial parts of the parents while mutating certain instructions, which may or may not end up making the child programs more fit. So in this example, you can see how one parent has contributed its first 5 genes down into the child program, where the child has inherited the next 5 genes from a second parent. Likewise, a mutation has been applied to the third instruction from the right at the end of the child genome. You can see how it was a value of 0.9, which corresponded to an upshift operator. This has been mutated to a 0.8. This small change has resulted in a corresponding change to the instruction from becoming an upshift operator to a downshift operator, which may or may not make that program more fit than the others. The final step of the process is that the resulting programs that are generated get ranked according to how well they've performed. You can see in the slide how the top program fails and is removed from the pool of genomes. However, the bottom program succeeds and is carried forward to produce child programs. So it just so happens that the bottom program is a valid running program that takes 1 byte for input and increments it and prints it out twice. The top program, that was eliminated because all it appears to do is the first instruction takes input from the user, that's the comma. The second instruction is a terminate loop command, the close bracket. Since a loop hasn't even started, this would likely cause a Stack Overflow exception, causing the program to terminate prematurely. Since the top program has done very little except for take input from a user, it would likely have a very low fitness score, if not 0, which is why it would be most likely eliminated from the pool. While the second program executes completely and even outputs characters to the terminal, which would likely get scored higher in the fitness ranking. And so now what everyone's probably waiting for is to see some of the results that the system has produced. AI programmer has been able to produce results that can produce a program to output hello world. It can write a program to reverse a string. It can perform addition, subtraction, multiplication. It can take user input. It can even output the Fibonacci sequence from 2 starting input values, a really fascinating example I'll show you in just a few moments. And it also wrote a program to output the bottles of beer, a famous campfire singing song. So with these examples, let's take a look at a closer look at some of these examples. This is a very early version of AI Programmer. It was instructed to produce a program that can output the word hi, H-I. It wrote this program in 1 minute. It took it 60 seconds, starting from a completely blank state to create the program that you can see there in the second yellow box highlight. That's the program it created. It indeed outputs the word hi, followed by a bunch of random ASCII characters. This is a great example of be careful what you ask the AI to do because it just might do it. So it was only instructed to output the word hi, to write a program to output hi, and nothing more. And so the AI did indeed that, followed by a bunch of random garbage, but it still solved the problem. I like to compare this to building a robot that its job is to cook you eggs in the morning. And after it cooks you eggs, it spins around in a circle and its head pops off. That's an example where it's completing the task that was given to it, but it might have unnecessary or unintended consequences. So we do have to be careful. Here's another example. The AI programmer was instructed to produce a program that can output the word hello. It produced this program in 29 minutes. Again, notice the random ASCII characters. This is an early version of the system and a quickly designed fitness method that didn't account for the random characters afterwards. In fact, the program even ends with a Stack Overflow exception, where the system was likely taking advantage of an exception to terminate the program earlier rather than to execute unnecessary instructions afterwards from which it would receive a penalty upon. So terminating the program with an exception was actually an advantage in this circumstance. Here's a more recent version of the program of the system, which was instructed to create a program that would take input from the user and output the word hello, followed by the input or the name. So here you can see the program that it generated is much more complex. It's longer, it contains a lot more instructions, and it generalizes. So the program that was created will take input from the user, any input that you type. It will then concatenate the word hello, followed by the input from the user. So this is a much more advanced type of program, and this is generated in 30 minutes. Here's another example. AI programmer was instructed to create a program that would output I love all humans. It was also instructed to clean up any random characters afterwards and to only output the exact string. You can see this is generated in 10 hours. This is a much longer program, and it indeed output the instructed target sentence, as well as a totally clean response with no remaining characters afterwards. Here's an even more powerful example. This is the bottles of beer on the wall song. So the AI programmer was instructed to create a program that would take a numeric input from the user, which would be the starting value, and then loop down, counting down from that value to 0, outputting at each interval the number followed by the phrase bottles of beer on the wall. So it would go 99 bottles of beer on the wall, 98 bottles of beer on the wall, 97 bottles of beer on the wall, counting down to 0 until you can see in this example, it actually wraps around and hits 255, which is the max value for the byte, which is the memory storage maximal value. So it does indeed count down from 5 to 0. This includes several key programming concepts that it generated this in 33 minutes. One is accepting input from the user. The second is taking numeric input from the user and converting it to ASCII in order to concatenate it to text. The second is outputting the text, or sorry, the third is outputting the text, followed by a conditional. It needs to know when to terminate the looping, as well as performing a loop and iterating down the sequence. So there's a lot going on here that come together, a lot of programming concepts that I was able to create this program for that you can see in the slide in just 33 minutes. Here's a close-up of the program Hello. This was generated in 29 minutes. You can see the dot operators are output operations, and there are indeed 5 operations of dots, which correspond to each of those characters in the word. That will output the word hello, generated in 29 minutes. Here's an example of addition. This will take 2 input values from the user and add them together and output the result. This was generated in 45 minutes. You can see the first instruction, the comma, is a user input command, followed by an upshift operation and another user input command. The upshift operation has the effect of storing the user input in a memory variable. This is the way that the programming language uses to store variables. And this is generated in 45 minutes. Here's the Fibonacci sequence. This is one of the most incredible examples. So the system was instructed to create a program that would take 2 starting input values from the user, which would be the 2 starting Fibonacci sequence input values, followed by outputting the Fibonacci sequence up to the max value of 255. This program indeed performs the Fibonacci sequence. Again, you can see that pattern of input, upshift, operation, input again, followed by a bunch of code that successfully outputs the Fibonacci sequence. This was generated in 7 hours. Now, this is using a modified version of the programming language that I created, specifically being suitable for genetic algorithms and evolutionary processing. So it contains a couple of extended programming instructions, such as the ability to support functions, the ability to support fast cell initializers, which compress the series of pluses or minuses to increment or decrement the value in a memory variable, as well as storing global values, which is the $ operation, and retrieving stored values, which is the exclamation mark value. These programming instructions are detailed later on in some of my work and my website, if you're curious in reading more about that. It's pretty amazing how the AI was able to produce all of these programs and more. There's certainly some potential what can be done. I've been writing software for many years, and I've always felt it's just something that humans shouldn't be doing. Humans should be designing the programs. Computers should be writing the code. So consider a future where humans create building blocks of program designs. They give these designs to the computer, which then writes the programs to make these building blocks real software. The human can then design higher level problems, where the computer can then utilize the building blocks as submodules to create even more complex programs, generating software for web applications, databases, games, and much more. I always like to include a recent example of AI programmer producing a result. So here I wrote this in just a couple days ago. AI programmer was asked to create a program that would output the phrase, "Thanks, 2021, GECCO and EvoSoft." This is the most recent version of the system, and this program was developed in 30 minutes. And this concludes my presentation. I'm very passionate about artificial intelligence and data science, and especially using evolutionary techniques and genetic algorithms for program synthesis. If you'd like to read more about this work, please visit my website at primaryobjects.com, where I go into all the background and history of this research project, as well as the programming language and the extension of the language that was created for this work itself. You can contact me on LinkedIn or Twitter. And with that, I'm open to questions and comments. Thank you very much.